So before you get started on your lesson for 1.1 functions, we are going to review one of these quadratic application questions. And I know there's a few on your homework, but there is definitely one on your test. And we'll talk about where we typically see mistakes, so that way you guys don't make that mistake. So Sari is going to make some sales calls to stores. So she's going to go and visit and try to get some sales. If she visits 12 stores, she can sell 60 boxes per store. So this is just a warm-up question. You don't have it anywhere on a paper. But that clue I'm going to go ahead and put in this chart. So 12 stores, she sells 60 per store. And have you guys caught on? You actually don't need to fill in this part, because we're not really going to use these numbers at all. We're going to be using the algebra component and then our calculator in a minute. I think it's 720, but whatever. So if she makes an additional sales call, so she visits one more store, so 13, her number per store is going to decrease by 3, so she's down to 57. So again, you could multiply this together and get this number, but it's not going to make a difference. What matters for me, can you set me up some algebra that represents number of stores she visits and also the number of boxes sold per store based on how many increments we've had here? So Sari starts with 12 stores, but then we keep adding what? What's the increment here?
1.
We're adding 1, so you're going to add 1x each time. And then here you're going to start with 60 boxes per store. But what's the increment there? Yep, we're dropping 3 each time, so it's minus 3x. So on your calculator, I need you to get this typed into Y1. And they want me to maximize her revenue. So what I'm going to do here, I'm going to highlight the question because I really want you guys to connect this. So find the number of stores to maximize. All right, I'm going to pause the video for a moment. So even though it's not the best window, we can see the maximum of our quadratic. So we're going to find the maximum by doing second trace. Whoops, second trace. And then choosing maximum. And going left of the vertex. And then right of the vertex. And then the ordered pair, I would like you to get in the habit of writing down the ordered pair, but this is where we're going to have issues. So, I already forgot what it was. Was it 4, 7, 6, 8? Okay. So, this is not an acceptable answer, because I go back to the question and it says, find the number of stores that she should visit. So then the next thing a kid writes down is, oh, well then the answer is 4, because that's x, and I'm always supposed to find x. But that's not quite what's going on here, guys. Remember, the number of stores is an algebraic expression. The number of stores that she visits is found by this. So 12 plus x would be 16 stores. Very good. So just make sure before you finalize your answer to that question on the test, and this is next week's test, by the way, that you are not answering the wrong question. All right. In the new packet, it's got a very generic name, functions. Actually, the whole unit is called functions, but it's functions from a calculus perspective. So that sounds scary, right? From a calculus perspective, what could that possibly mean? So it's going to be a lot of new vocabulary for you, and maybe some old vocabulary, but with a different notation. So this first question, or this first concept here on your notes, they're talking to you about how they subdivide the real number system. I have good news for you. We are not going to discuss imaginary numbers for like the next month and a half, except when you're taking a quadratics test. So for this unit, we don't really discuss anything with complex numbers and imaginary numbers. So in the real number system, they can be split into rational and irrational numbers, and then further split down into what are called integers, whole numbers, and natural numbers. And like everything in math, they have common symbols that represent all those things. But just so you guys know, because sometimes they do throw this vocab on standardized testing, start with the first numbers you learned as a small child, the natural numbers. What do you think the natural numbers are? Think of like when you're 3 and 4, what do you first learn? 1, 2, 3, 4, yes. So it's your counting numbers, starting at 1. Because small children don't really think numbers exist before, or like they have a very small window of numbers that they're working with. And then when you go to like kindergarten, then they introduce you to somebody else called 0, and that creates the whole number system. So it's the natural numbers plus 0. So 0, 1, 2, 3, 4. And then they really blow your mind when you're like in 2nd grade and they go, did you know there's negative numbers? You're like, what? So that's the integers. That's like -3, -2, -1, 0, whoops, 1, 2, 3, and so on. And then you learn that numbers go on forever. Well, that's freaky. Yeah, what is the point? That's exactly what I'm thinking as a small child. And then these numbers can be subdivided between rational and irrational. So the root word for rational is ratio, and ratio in math means a fraction. So rational numbers can be written as a fraction, which mean irrational numbers cannot be written as a fraction. So give me some examples of rational numbers, things that either are or can be written as a fraction. 2/3, does that work? How about 4, is that rational? Yeah, because you can write as a fraction. Same thing with 0, you can always write that as a fraction. You know, the list is pretty intense. What about, this one always gets kids, the 0.666 with the repeating 6 on it. When there's a pattern, that is rational because repeating decimal patterns can always be written as fractions, so that is rational. So what are some things that are not rational then? What are irrational? Pi, everyone's favorite number, pi. You know any others? You actually know a lot, you just never think of them this way. Think of the ugly decimals that you get on your calculator that you can't do anything with. Like the square root of 7. Like I can't work with that. Like if you typed it in, it's gross. And it goes on forever and there's no repetition. And then if you're curious, my favorite irrational number is the natural number e. I know you were all waiting for that one. Did you know e was a number? Remember natural logarithms? They're base e. It's a natural number. Okay. Not to be confused with the naturals. Totally different. I know. Way confusing. So this is a nice diagram that you've probably seen in every textbook you've ever had in math for algebra and beyond. It's in your book as well. So it's showing you how like all the natural numbers exist within all these other qualifiers as well. So if they ever put a trick question on an entrance exam for a college of like, give all the classifications for the number 2, like there's a lot of answers. It's natural, it's whole, it's an integer, it's rational. So be careful on those questions. Again, from your textbook, they gave you some nice examples. All right, your textbook, because it is college preparatory, so it's prepping you for calculus. They are big fans of what's called the set builder notation, which you have probably never seen before, and we aren't really going to use. But what I want to do is I want to show you how to read set builder notation, just to understand that it is out there. You might see it. I don't think Mrs. Gupta even uses it in calc, but when you move on to college, I don't know what professors you're going to get, so I just want you to be exposed to it. We use what's called interval notation. So that's the thing with the infinities and the brackets and the parentheses, and we did a ton of this in Algebra 2. So we are very good at interval notation. Just remember that it has to move from least to greatest. Anytime you give me an interval in math, it has to be least to greatest. And we have to be careful with the usage of parentheses versus brackets. So when do you use a bracket? Any thoughts? So a bracket is used when you actually have, like you exist at that number. So like you start at 3 because 3 is part of your solution set. But a parenthesis would be used if you can't actually use that endpoint as part of your solution or as part of your interval. So like we're going to see an example coming up where there's an open circle on a graph. And because the open circle indicates that you don't actually have a point there, you have to use a parenthesis. The other place that you always have to use parentheses, and remember this guy, is when you use infinity and negative infinity. You always have to use parentheses on infinity. Anyone want to take a stab at why? We're going to get really deep here for a moment. Huh? Because it never ends. So to indicate that you are going to somehow land on infinity is preposterous. You can't get to infinity, y'all. It's a concept. Oh, man. Go tell all your friends that at lunch. You'll be the most popular kid, I swear. All right, set builder notation. Ready? If I gave you this inequality, x is, now I have dyslexia, so help me with this. What symbol is that? Greater than, okay, so every time, even to this day, I have to stop and make sure I'm not doing it backwards. X is greater than 18. So for us, this is how we would write the interval. Parenthesis, 18, comma, to infinity. So all my numbers greater than 18, notice how they did not use a bracket on 18. Tell me why. Because it doesn't have an equal to bar, so 18 is not actually part of your solution for that interval. This, my friends, this is what your textbook likes you to think about. Okay, let me translate this for you. Ready? The solution is the set of all numbers such that, that's what that means, such that your numbers are greater than 18 and your numbers are components of the real number system. Yay! So can we just pretend we don't need to do that for at least a few years? And if you have to start writing your answers in set builder notation in the near future, it's really not that bad, guys. The only thing that changes is this part. So it's not that complicated. It's just a lot of stuff to have to write down. So you'll notice when you go to college, you're going to get some very set in their way professors that want answers a very specific way and will not accept it otherwise, and you just kind of have to adapt to that. This is a diagram from your book, and if you're not sure how to go from what we call inequality to interval notation, this would probably trigger your memory a little bit. And I know in my Algebra 2 classes, when we see a problem like this, I used to call these sandwich inequalities because your solutions are sandwiched between two endpoints. But the usage of parentheses versus brackets, hello. Okay, that is a big problem in Algebra 2, and I expect at our pre-calc level that we don't make that mistake anymore. If you're supposed to use a bracket, you better be using a bracket. And it's considered a concept mistake in this course if you use the wrong endpoint. So be very careful on that. All right, so read this to me. X is less than or equal to -2. Now, if you need it, and sometimes I do, if I'm having a bad day, I got to draw it out. I have to draw out -2, and then I think of it as an arrow going less than -2. And then am I supposed to include -2? Yes, so I would have written a bracket. This helps me create my interval. You guys do not have to graph it at all. But I do need the interval, and the interval must be least to greatest. Otherwise, you are making a concept error. So where does your shading solution set start? What's way down here on a number line? -infinity. And then all your solutions keep going until you hit what number? -2 with an inclusive bracket. If you get that interval backwards, you're wrong. And that's a big mistake for pre-calc, so we have to be real picky about that. So this one, this must be greater than -8.8. So if you wanted to graph it, you sure could, but I noticed that my interval will be starting at -8.8 this time. Am I going to include -8.8 as my solution? So I need a parenthesis, very good. And then it's going to keep coloring in all the line until infinity, very good. And we always use parentheses on infinity. All right, this is one of those sandwich questions. So you can read this one of two ways. I read it as all my solutions are between 5 and 15. That's how I read it. But you could also read it as, what does this say? Be careful. X is greater than 5. You see it? It's backwards. So this is actually, solutions are both greater than 5 and, what does this say? Less than 15. So what are your numbers that are both greater than 5 and less than 15? Well, that would be from 5 to 15. So that's why I like to translate that in my brain to solutions are between 5 and 15. It just makes more sense for me when I read a sandwich question that way. Now here, this is the one where when they taught this to you in Algebra 2, you were like, what? This was your first taste of really crazy notation. So -11 comes before 1 on the number line, so let's get that straight. I'm supposed to be graphing solutions that are both, or either, less than -11, so down here, with a parenthesis, or anything greater than or equal to 1. So your job is to figure out how to write that as an interval. And we know intervals always go from least to greatest. So where does your interval begin? -infinity to -11, which we do not include. Oh, what do I use to join two intervals together? A union symbol, very good, which is simply a U without a tail. I am going to make fun of you if you put a tail on that, because that is silly. Just a union symbol, not a U. And then it picks up again at 1 with a bracket, and then keeps going until infinity. Whoops, I need a parenthesis. There we go. Remember those guys? So when you ever have to jump over numbers in a domain interval or any sort of interval, you have to use that union symbol to join up your intervals together. Otherwise, this is one of those things in math where, like, when you're a younger child, like, you kind of sort of got it right, and your teacher was like, okay, pretty good. But now in PreCalc, like, we have to get it right, because otherwise what we've just written down is nonsense, so we have to get everything in the right order. Okay, a little bit of review. Domain versus range. Do you remember what domain represents? Which, is it X or Y value for domain? It is X, very good. How about range? Y. Okay, science buffs. Which is the independent variable? X or Y? It's the X. The x-axis is typically the independent variable because that is what you as a scientist choose to change, and then you measure it for the y variable, which is why it's dependent. You measure the outcome, I should say. Okay. Children who've had me in class before, this is the boys and girls metaphor of domain and range, which I'm not going to discuss because I don't want it to be recorded on the internet. When the mic's off, we'll talk more about it. Okay? Alright. Actually, So in order to come up with whether our relation is a function or not, think of this as x and y. Every x can only be paired with one y. Well, come on, buddy. B. So in this example, okay, my pen's not working. In this example, every x is only paired with one y. There is a y that's paired twice, but that's not the way the definition works. It's every x can only be paired with one y. All right. So yes, this is a function. And if you had to explain with rationale, which we do ask you to do, your explanation would be every x is only paired with one y, or every input only has one output. The domain would be a set of all of these numbers. So notice what they did here, guys. They used what's called set notation. So you can't use parentheses and brackets if it's not an interval. So if you're just listing numbers like we did here, you have to use these squiggly brackets. Start practicing those, okay? Those are going to be set notation brackets. So if you're just listing them out. And then same thing with range, although for some reason they left off the 7. I'm not really sure why. Because it should have been listed. It is a component of the range. However, it is not paired up with any x. I don't know. That's a weird example. Whenever I give you an example like this, they'll be paired up accordingly. Okay, this is not on your paper anywhere, but this is a good review from Algebra 2. You guys told me that domain is a listing of all the x values, and we know if it's connected and continuous like this, we have to write it as an interval. So this is a case where you're going to tell me where the domain begins and ends using interval notation. So, right here, that's the beginning of our domain. And it starts at -5. However, did you guys notice, I know it's hard to see in the back, did you notice that there's an open circle on that endpoint? And there's no other ordered pairs along x equals -5? So that means I have to start with a parenthesis. And then the function continues on until it stops right here at 5. But notice, there is an endpoint there at 5. So since an x value exists on that function at x equals 5, here we have to use a bracket. So the domain stretches from -5 to 5, including the 5. The range, however, we know are the y values, and you must measure low to high. So this gets kind of confusing for kids, because when I look at the lowest portion of this function, there is an open circle here, but if you keep looking across, there are several points where it does hit y equals -2. So your range does start at -2 with a bracket because there's at least one ordered pair at -2 for y. And then the range stretches up, up, up until it stops at +2. What do you think? Bracket or parenthesis on that? I heard bracket. Thank you. There are several ordered pairs here at 2. So we count it with a bracket. And then I kept calling this a function. That was a little bit of a spoiler alert. Is this a function? Yes, because this passes the vertical line test. Remember that guy? I think I skipped a slide. If you draw a bunch of vertical lines through your relation, if each vertical line only touches the function once, or the relation once, it is a function. That actually goes along with the every x only has one y idea. Oh, this is the slide I skipped. This example here, this is a function, but what if I added another ordered pair right here? So like what if this is the ordered pair 3, 2, and this is the ordered pair 3, -1? So I can see it fails the vertical line test very clearly, but the other reason that you could say that it's not a function is because x equals 3 is paired up with 2 different y values, or it has 2 different outputs. That's what makes it not a function in that case. All right, 12. Domain. How far left are we looking here for our domain interval? Can you tell? -4, and there is a point there, so it's a bracket with -4. And then the furthest to the right it's going to reach is right here at 3. However, there's only an open circle there, and there's no other ordered pairs. So we need to use a parenthesis. The range starts way down here at -5. But the only thing I have there is an open circle, so you got to use a parenthesis. And then it stretches all the way up until +5. And again, there's only an open circle up there, so you have to use another parenthesis. So -5 to 5, not including the endpoints. And then is this a function? No, this is very clearly going to fail the vertical line test. So no, not a function. What do you think about the old mistake from Algebra 2 of getting your interval backwards? Especially for range. I used to get kids get the backwards interval. So like they'd say 5 to -5. Is that going to be correct? No. And that's a very big deal in PreCalc because we're supposed to be masters of this by this point, you know, by the end of PreCalc. So when you get intervals backwards, we're going to view that as a concept mistake. So watch out for that. Okay, domain. Now this one has arrows on the end, which indicates that it goes like this forever. So when I go to figure out how far to the left it's going to stretch, I'm not really going to have a lot of luck because it goes off to -infinity in the left. And then it keeps going to the right forever. So that domain was all real numbers, -infinity to infinity. However, the range is a little different. He does go up forever, but there is a definite starting point for your range. Can you tell where it starts? It's at -3. And since there are several ordered pairs there, it starts at -3 with a bracket and then goes up forever. Is this a function? Yes. Passes the vertical line test would be justification enough for me. But word of caution, on your homework, there's going to be questions where it's going to ask you whether it's a function or not. And what I don't want to see is, yes, it's a function, it passes the vertical line test, without you actually graphing me the function. So if I didn't give you the graph, and you're claiming it's a function because it passes the vertical line test, then I'm going to need you to draw the graph. It doesn't have to be beautiful, just sketch it. But you have to show me that you know what it looks like. I used to get that a lot from Algebra 2 kids. They'd be like, well, it's either yes or no, so I'm just going to throw yes down, and then I'm going to say passes the vertical line test and hope for the best. So here in PreCalc, we need you to show that it passes the vertical line test, please. All right, so quick, these are not on your paper anywhere, just for funsies. Can you all on the back see this? I'm sorry. The x's are -8, -5, 0, 3, and 6. And then they're paired up with various y's. So is that a function? It is a function because every x is paired up with just one y. There are a couple of y's that are paired, or yeah, there's one y, -3, that is paired twice, but that's not the way the rule works. It's every x can only have one y, not the reverse. C, is that a function? Clearly not, and the reason is it fails the vertical line test. You can abbreviate that with VLT. Now this example here, they're going to ask you to think algebraically for a moment. So y squared minus 2x equals 5. They isolated for the y and they came up with this equation. Y equals plus and minus square root of 5 plus 2x. So you guys aren't real familiar with what this looks like, but we're going to learn next semester that this is a sideways parabola. I don't know exactly what it looks like, but it looks something kind of like C. So right away, you would have told me if you knew what the graph looked like that it fails the vertical line test, so no, it's not a function. However, you guys wouldn't know what that looked like because I've never taught you. So unless you could somehow magically figure out what that graph looked like, you'd have to use another technique for proving to me that it's not a function. So this is what they're saying. They're saying one positive and one negative solution is going to show up for every x value. Think about that, guys. If you plug in my favorite number, 7. If I plug in a 7 right there, I'm going to get the square root of 19. But it's positive square root of 19 and also negative square root of 19. So that was a great sound. And that was just one case of the x equals 7 or some x giving me 2 different y values. So that's a way that I could prove that this is not a function. And I would have to show at least one set of ordered pairs where the x was paired twice. So that's kind of a pain, but there is one on your homework that's a little more obvious than this one. But you can give me at least one nice example of, okay, here's one x giving me 2 different y values, so therefore it's not a function. All right, the input value is a student's ID number, and the output value is a student's score on a physics exam. So in this case, I don't know if this is on your paper anywhere, I think it's just on the board. So the x's are the student's ID numbers. So think of it this way. Each student ID number, can you assign 2 different test scores to it for a physics exam? No. I mean, they can retake it, I suppose, but just when they're taking it one time, you're going to get 1 score. So my next question would be, is this a function? And then yes, because every student, every x, is only going to be assigned 1 test exam score. Okay. All right, we're back to your notes, guys. Vertical line test, we talked about that already. Looks like you're professionals at vertical line testing. Excellent. But please make sure, guys, that if you're claiming the vertical line test is either passed or failed, you need to show me that, unless I already give you the picture. Okay, back to your notes. Function, f of x. Here he is. I want you to find f of -4. Talk to me like I'm a little kid. What do they want you to do? Plug in -4. Very good. So please do use your calculator. Just get in the habit of writing the skeleton of your function and always using parentheses with whatever you are substituting inside. So in this case, it'd be a -4. No mental math today on this one, guys. Just plug it in. I think I heard -172 from the last class. Does that work? Yep. Awesome. So similar here, guys, but this time you're going to be kind of out of luck on your calculator because we're not substituting in just a value. We're substituting in an algebraic expression. So if you're plugging in a 2a this time, you have to use your thinker a little bit here, guys. Let's talk about order of operations. You have to perform the exponent first. So 2a to the 3rd power is going to be an 8a to the 3rd. But you still have to multiply that term by a 4. And then 2a squared, this term, is going to become a 4a squared, but you still have to multiply it by the 6. And then 3a times 2a, that's just 6a. So finally, when you go ahead and simplify, there's no more like terms, you just got to write down a simplified coefficient here. 32a to the 3rd plus 24a squared plus 6a. And let's see, I feel like you guys can find a little bit of space. I know there's not tons of space, but in example 1, we didn't really write anything down there. Can you write this question down? So same function. There's one on your homework where they want you to do like a plus 2. So when you see this, you should get a little bit sad, because look what we have to do. For a plus 2 to the 3rd power plus 6 times a plus 2 squared plus 3 times a plus 2. And at first glance, you're like, okay, that doesn't seem too bad, except I want you to really think about what this means. A plus 2 to the 3rd power is not a to the 3rd, 2 to the 3rd. You don't distribute like that. A plus 2 to the 3rd power is a plus 2 times a plus 2 times a plus 2. Yeah! All right. There's more to this problem, right? All this would come down. But I just want to talk about how you expand a plus 2 times a plus 2 times a plus 2. There is a shortcut using Pascal's triangle, but none of you probably know that, so we can't use it. So instead, we have to like FOIL this out, but you got to do it in stages. So I always taught my kids to multiply the back two binomials together. So that becomes a squared plus 4a plus 4. But then you still have another a plus 2, and then you still have the 4. So from here, and we're not going to work through this whole question. I just want to warn you, there's one question on your homework that is almost identical to this. So you're going to have like this much work on your paper. You guys still have to distribute the a, you have to distribute the 2, and then at the very end of that, you got to go back through and distribute the 4. And then you have to remember that there's all of this part also. So I'm not kidding, guys. That work on that one problem is going to take up like half your page. So keep with it. You can do it. I just want to give you a heads up before you get to your homework. Okay, we're going to, not permanently, we're going to temporarily skip piecewise. So at the top of worksheet 1B, we're coming back to that on Monday. Because everybody loves piecewise, right? And I would like you guys to skip down to the section where it talks about implied domain. So if you have to come up with domain or domain restrictions on an algebraic function and you can't use a graphing calculator to help you out, or possibly the function is so strange that the graphing calculator doesn't actually help you, you have to know how to find them algebraically. It's not bad. There's two things you have to watch out for. The two things are even radicals. So what I mean by that would be like a square root or a fourth root. Remember how there's different types of roots? We typically use square roots in Algebra 2, but there are others. So square root, fourth root, sixth root. Or if there's algebra in a denominator. So if you have a variable in the denominator of a fraction, you have a problem, and we got to find it. Okay. So write yourself some other notes down here, guys. If you have an even radical, here's what you have to do. So like you'll have the square root of like some junk under here. So you take the algebra inside and you tell me that it has to be greater than or equal to 0. So think about that, guys. If you took the square root of something that wasn't greater than 0, that means you're trying to take the square root of something negative. What happens when you take the square root of something negative? You get i's. And I just told you we're not talking about i's for the next month. So you're not allowed to have i's in your work in this stuff. So that's the restriction that we're going to set up, okay? The other thing you're going to run into is the denominator issue. And if you have a denominator with algebra in it, what you do is you take your denominator. So like you'll have a fraction, you know, you have something in the denominator. So you take your denominator, come on. You'll take the denominator, and you're going to tell me that it cannot come out to 0. And then you're going to solve that. So you're going to say, like, whatever this stuff is can't be 0. We're going to solve it, and we're going to get 2 restrictions. And then, of course, it's going to get exciting. So hang on for some examples. Here we go. This first example, do you see any square roots or fourth roots or sixth roots or anything? No, so we don't have to worry about the radical thing. Do you see any denominators with algebra? Yeah. So this guy right here cannot be 0. So what I would like you to do, guys, change this to a cannot equal symbol. But we're still going to solve it like we would solve any other quadratic. So I think about all my methods for solving quadratics. This is a great one for factoring. So x squared minus 6x, you can factor the x out, and you say x times x minus 6. And instead of can equal 0, we're going to say cannot be 0. So then you take your two factors, which are this and this, and you tell me they can't be 0. So x can't be 0, and then this one would be x can't be 6. But we're not done, because we're pre-calc, darn it. We can't say x can't be for a solution. We have to write this in interval notation. How do you say every single number on the planet except for 0 and 6? Well, we know our intervals start at negative infinity unless I'm told otherwise. So negative infinity, and then every number is good until you hit your first problem. What's our first problem? 0. But you just told me I can't be 0, so what symbol do I put on 0? A parenthesis. Now, I need to hop over 0 and get to the other side of 0, so I'm going to use a union symbol, and then I'm going to start my next interval on the other side of 0, and then I'm good until I hit my next problem. What is my next problem? 6, but I can't use 6, you told me that, so put a parenthesis on it. And then you got to hop over 6, get to the other side of it, and then keep going until infinity. Woo! Thanks, math. Couldn't make that easier, could you, math? Nope, we're going to write interval notation. I saw the hope in your eyes when you said, oh, she's going to do that thing where she gives me an easier way. No, I'm not. Got to do it that way. All right. Hey, fun fact, guys, if you don't have either of those restrictions, that means there are no restrictions on your domain, and therefore it is all real numbers. Don't worry about range on this section. I just want domain. Guys, do you see any radicals?
No.
Do you see a denominator with x in it?
No.
So is there any restriction on your domain? Nope. So it is all real numbers. Negative infinity to infinity. Uh-oh, number 11. Do you see a radical?
Yeah.
Is it even? Yeah, because this is like a square root, right? So what we have to do is you take your algebra inside the radical, and you tell me that it has to be greater than or equal to 0. And then you solve it. So pull out your Algebra 1 brains. We're going to add the 2. And then what happens when you divide by a negative 3 here, guys? It flips. Yes, yes. So x must be now less than or equal to negative 2/3. But guys, that's an inequality, not an interval. Your domain, how would you write all numbers that are less than or equal to negative 2/3? So negative infinity up until what number? Negative 2/3. How about the number negative 2/3? Do we count it? Do we not count it? Count it. Let's put a bracket on that baby. Woo! Real quick, 13. I see a denominator. So I say my denominator cannot be 0. Don't you think that's a beautiful one for factoring? Isn't that just x minus 5 and x minus 3? So if x minus 5 can't be 0, that means x cannot be 5 and x cannot be 3. Uh-oh. Alright, start writing the interval, guys. Negative infinity to, what's my first problem? 3. Jump over 3. 3 to 5. Jump over 5. 5 to infinity. Very nice. Alright, you got your first book assignment. Oh, we need to change it though, guys. Where it says 37, scribble that out on your blue sheet. We're not doing 37. You're going to do 30 instead. That's a better problem than 37. Like literally better, not worse, I promise. So you're doing page 9 and 10 assignment. Starts off with 7, 18, 19.